Good morning. Today we are going to see a problem which is on column, and this we are going to calculate directly. So we have designed an internal RC short column G10. So we have here, sorry, C10 for a G plus 2 storied building as shown in figure for the following data. This diagram that is given for the question in examination, I have taken another data. Diagram was given from the examination. So different values are given: floor finish, live load, floor to floor height, height of plinth above ground level, depth of foundation below ground level, thickness of wall, density of masonry, width of column, thickness of slab, and use. So actually M25 and FE415. So I have taken this value, that is, instead of 25, I made the calculations by using M20. So I will just make this value, that is M20. So this I will take it as M20. So now we will go with, so C10. So we are with this column which was shown over here. So this column we have to design, C10. So now I will consider only the part that is, or the slab which is around this C10. So we have this slab around C10. That is S1, 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 S1. Now we have this dimension 3000, 3200, 3540, 3650. So we have, these are the dimensions of the slabs which are around this C10. So now when we will design this slab, so we have to take the area, we have to divide this into four parts. We have these four columns, C1, C2, C10 and C9. So we will divide it into four parts, and that each quarter will go to that column. C1 will be with this portion, C2 will be with this portion, then C9 with this portion, and then we have C10 with this portion from this slab. So I will mention it as slab 1. Now from slab 2, again we are in the same fashion. We have to consider that quarter in this portion. And we have this value, we are in this fashion, second. And similarly, we will go for this third, and then we will be with, this will be third, and this we are with fourth. So we are going to consider the area that is around column C10. So we have this area which is around column C10. So we have to consider area, this portion which being hatched around C10. Now, what are the dimensions? So now you can see we are with this. So I have taken this portion which is hatch portion, that is to the larger scale on this side. Now you can see we have this column C10 and we have to go with this slab 1, 2, 3, 4. Now we will go with this distance. Now half of this. Now you will understand this quarter of this. Means we have this dimension, half of this, 3540 divided by 2, that comes 1770 millimeter. Then this portion we are considering first. So we have this value 1770. Then we have this value 3000. So this value comes 1500. So we have taken this value, 1825. So we will have with this second. So this portion, this is till center, actually all these values are till center, and we have this value 3650.2, and we will get it as 1825. So we have this value 1825. Then we have, this is 3000, so this distance will be 1500, and we have, this is 3200, and so if I will go with this, then we will get it as 1600. These values again we have 1770, And then this second value we have again 1825. So vertical values, this is 1600, and we have this will be 1500. So this total distance, if we will see, so we have this distance that is equal to 3.1 meters. And then we have this distance, if we will calculate it, then we have 5, 9, 3.595 meter. So we have this rectangle having dimensions 3.1 meter and 3.595 meters, and that we are going to consider now area of slab from which load is transferred to this C10. So now we have this 3595 millimeters and 3100 millimeters. So this is first part. So now from this we are going to calculate the area of this slab. What values we will get? So we will write area of slab transferring load to column C10. Area of slab transferring load to column C10. And what are these values? So we have this is 3.595 into 3.1, and we will get this value that is of slab is 11.1445. meter square. So area of slab transferring load to column. So first we will get it as 11.1445 meter. Then we will switch over to the wall. So the column C10 or the load on column C10 from the wall. So again we have these four walls are connected to the column. So we are going to consider again half from this. So each half from this, half from this, half from this, and half from this. So this total length of the wall will transfer their load to this column C10. So we will go one by one. So this is first having value 1600 millimeter. Then second we have 1500 millimeter. We can have 1600. We can have 1500, 1600. Then 1770 if we will divide it, and then we have 1825. So this total length of wall or weight of this wall will be taken by this column C10. This is approximate method. So if I will calculate length of wall transferring load to column C10, and then if we will add this, then we have 1600 plus 1770 plus 1500 plus 1825. And then we will get total length of this wall that is equal to 6695 meters. And once we have these value millimeters, once we have these values, then we can design the column C10. So now first we will write. So we have area of slab transferring load. So I will write only area of slab, which is equal to 11.1445 meter square, and length of wall contributing to load on column C10 is 6.695 meter. Now we will find total load on it. So now we have first load from slab. So what is load from slab. So same we have seen when we are going to design the beams. So 25D plus floor finish plus live load into area of slab. Into area of slab. Now thickness of wall, thickness of slab is given 0.12. So 25 into 0.12 plus floor finish is 1 and live load is 4 into 11.1445, and then we will go get this value of the load from slab to column 89.15 kilonewtons. So this is number 1. Now we will go to the second, that is load from wall. So we have load from wall. So that is equal to density of machinery multiplied by width of wall multiplied by, that is width means thickness of wall, multiplied by height of wall multiplied by length of wall. Now this value we have given, that is 18 into 0. That is thickness of wall is 0.25, height of wall is 3, and length of wall is 6.695. So into 6.695, and then we will get this total load from wall 90.38 kilonewtons. This is two numbers. Then we have self weight of column. Self weight of column. Sometimes this is given, but if wall load area is around 10 to 15, then you can go this size. Width of the column is generally equal to width of the wall, and then I will go it as 300, or you can go 350 millimeters. Then we have, that is 25 into B into D into H, that is height of column. So we will get it as 25, B is 0.25, D is 0.3, and H is 3. So we have this total, if we will calculate, we will get it as 5.625 kilonewton. So we have this value 5.625 kilonewtons. So now therefore total load on column from one floor, so this is 3 number, from one floor, and then we have to add all this. So we have 89.15 plus 90.38 plus 5.625, and so if we will add all these values, then we will get it as 185.155. So just check it once. 185.155. So little bit here and there you can consider. So but add 1 plus 2 plus 3, 185.15 kilonewton. Now we have G plus 2 story, means we have 3 floors. So assuming terrace slab load equal to floor slab load. If nothing is given different, then we will consider same floor slab load. Now we have total G plus 2 stored, and therefore load from 3 floors equal to 3 into load from one floor. Load from one floor. And then we have this is equal to 3 into, we have load from one floor 185.155, and then we will get this value 552.6. 1 minute. So we have this value, just I will calculate it. So we have 3 into 185.155, it comes 555.465 kilonewtons. Now, load, or I will say self weight of column below plinth. Now try to understand this. We have plinth ground level over here. We have above this plinth level, which is of 0.5. Below which we have footing. Column we have actually, if I will draw it, so we have this will be column. And then we have below, that is footing. And this distance is given 1.25. So now if we will assume depth of footing as 0.5, then my total length, that is of the column below plinth, is 0.5 plus 1.25 minus 0.5. So just see 1.5. So it comes, that is equal to 5.5 gets cancelled, and we will get this value that is equal to 1.25. So this below plinth. So this is plinth level. And then we will get this value, that is 1.25 meters. And therefore we will get it as 25. B we have 0.25. Then we have depth 0.3. And then we have 1.25. And if we will calculate this value, then we will get it as 25.25.3 into 1.25. So 2.3438. 3438. And now we will have this as A and this as B. So total axial load on column C10. Total axial load on column C10 is A plus B, that is 555.465 plus 2.3438. And we will get this value, that is equal to 557.81. So we will have 557.81 kilonewton. So this is my value of P. So ultimate axial load. Ultimate load we have equal to 1.5 into 557.81, and we will get value of PU. This is equal to 836.71. 836.71 kilonewtons. Now in this, add allowance of 10%. So we have add allowance of 10% for unforeseen variation. For unforeseen variation. And therefore, we have to design, and therefore, design axial load now. Design axial load, and that is equal to 1.1 into 836.71. 836.71, and now we will get it equal to 920.38 kilonewton, and go on higher side multiple of 5. Therefore, design column for ultimate load, 925 kilonewtons. Now we will start with, we know that what is formula. We have seen axial load. So we have PU is equal to zero point 0.4 FCK AG plus 0.67 FY minus 0.4 FCK into ASC. Now put the values. So we have PU 925. So we have 925 into 10 raised to 3 equal to zero point 0.4 into 20 into size of column is 250 by 300 plus 0.67. Fy is 415 minus zero point 0.4 into FCK is 20 into ASC. Now check the answer. So I got value of ASC that is equal to 1203.48 millimeters square. So we will provide 206 bars. Therefore, provide 6 bars of 16 mm torque. And then we have to go for lateral ties or stirrups. Lateral ties. Then we have diameter. So two criteria we have. First criteria we have 1/4 of maximum longitudinal reinforcement diameter. So 4 mm. And second we have 6 mm. We have to take maximum of 2. Maximum of 2. Therefore, use 6 millimeter diameter. Then we will have next, that is spacing. For spacing, we have 3 criterias. Spacing, we have first criteria, least lateral dimension. Least lateral dimension, which is 250 millimeters. Then we have second, 16 into smallest diameter. So 16 into we have same 256, and third we have 300 mm. And we have to take minimum of 3. Minimum of 3. And therefore use 6 mm torque at 250 millimeter center to center. And then draw the diagram of the column, that is cross section. So we have 250 by 300. So we have 250 by 300. And then we have 6 bars, 1, 2, 3, 1, 2, 3. And then we have lateral ties. So likewise, we have to design this. So we have 6 mm tor at 250 mm center to center. And these are 6 bars of 16 tor. So likewise, we have to solve the problem. So now we will stop here only. So thank you.